where these structures or components are located. And also we will provide high-tech to verify the process.
We will also be doing the DCD approach there.
Right.
And both combination and all that stuff.
Yes.
Yeah, I'm just looking at the notes from the previous presentation. Sure. Okay. So you will be adding a concept. Can you briefly
Unfortunately, it's not our scope of work.
I think the comment from the past meeting was that the ITAC should be similar as to the ITAC that's already in there for the captain.
Yeah, and that's what we would expect to be, something very similar to that. I mean, we're working on the response now.
But this is a Cat 1.
Yes. And Howard, are you still on the line?
Yes.
Is there any, Dan has come forward, he's our licensing representative. Is there anything that you would like, and Flora is the one that's been working on this. Dan, is there anything you'd like to add about where we are with this right now?
I'm sorry, Jim, which slide are we on?
We're on slide 25, and the NRC viewers were asking about the ITAC that we're adding to verify the process, and I told them that the ITAC will look very similar to what we have for the current structures
Yes.
in the DCD.
Yeah, we have a first draft of that, Gina, and then we're trying to pattern that after the existing ITACs.
Is there a site plan in a way that is funded so you don't find it?
Pardon me, Dennis?
Is there a site plan where they show all the site piping?
It's not in the DCD, and I don't.
And the serial application also we don't have it?
No, I don't think we've worked to that level of detail yet.
I was having trouble hearing that, Gina.
Manus is asking if we have detailed drawings yet that show the layout of the buried piping and structures, and I was telling him that's a level of design detail that we haven't reached yet.
Correct, yes.
So it sounds like maybe for the people on the phone, and Dan, maybe you can answer as a representative, are you guys having a little bit of difficulty hearing us in this room?
Yes.
Yeah, I'm hearing, Gina, we're getting most of the folks, but sometimes people are far away from the microphone, sounds like.
Okay, so now Ruben has a mic that's close to him, and he's going to be doing much of the speaking for a while. So were you able to hear him talk about this slide, or does he need to speak up a little bit? Dan, could you hear him?
Especially when you talk closer to the microphone.
Yes. Needs to speak up a little.
Yeah.
Okay, I will.
Did you just hear that? Okay. We know it's hard, and so if you guys find Ruben taking a breath and want to say, please speak up or please repeat, we'd be happy to do that, okay? So did you guys have further questions on this slide?
No.
All right, Ruben?
Yes. The next question, 11 on section 372, is very similar to the one in 371 regarding the firewater service complex. The only difference, the actual situation is different, but the question is regarding control buildings, having the input motion for SSI analysis specified at the bottom of the foundation rather than in the bottom of the fill concrete, which is an integral part of the control building structure. We want to point out that the fill concrete is not part of the structure, it's just model in the structural model. It's a 16 feet thick as a 16 feet thick block of solid elements, which are embedded in weather rock with shear wave velocities ranging from 750 to 110 meters per second. So fairly, unlike in the firewater service complex, we have much stiffer material here. So what we did to address this issue, I mean, the concern was that basically the propagation of the ground motion from the bottom of the field concrete to the bottom of the foundation, there would be some filtering of high frequency content from the input ground motion. So in order to see if that is happening, we have taken the already presented results in the SR, where we have, for the control building profile, we have two firsts developed. One at the elevation of 224 feet, which is 1 feet below the bottom of the field concrete. And also we have one first developed at the bottom of the foundation. If you can go to the next slide, you can see comparison of these two first and also the ratio between them. And as you can see, because the material is stiff, we don't really, unlike firewater service complex, we don't lose any high frequency content. Basically, they're almost parallel.
So what is that red line?
Can you explain? Yeah.
Okay, the red line is the first at the bottom of the reactor building, for the control building, right?
First, at the bottom, that's the bottom of the basement, the red curve.
No, the red curve is bottom of it's 1 foot below the.
Okay, so that's at the bottom of the concrete. Okay.
1 foot below.
The green is bottom of the basement.
Right.
Okay, and this was taken from the SASE results.
No, this is taken from the FSAT.
These are the first.
Yeah, you have the figure numbers, the 200 and 200, chapter 2. This is what we found for now.
How did you compute? That's not documented, right? The red curve, why would you have documented? Or you just extracted it from your shape?
So if you recall, for calculation of the first for reactor building and control building, even though we consider two soil columns for them, we calculated at the same elevation in both soil columns and the envelopes.
Right.
Because these two buildings were next to each other.
Yeah.
So that's why we have the results at the elevation 224 for the C.
Oh, that's because you had it from the reactor building. Okay.
And it so happens that
and it just coincides with that elevation. Okay, now I get it. Okay, so you didn't have to go back to shake and get the results from there.
So what is the other one? That's the ratio of those two. Yeah, it looks very flat.
Yeah, high focus. All right, so it's basically propagates up the column without any dip. That's basically, right?
Without any dip,
you don't see a dip.
This is basically general self-amplification. Yes, exactly. So the same tool that is to demonstrate the high frequency, those components still remain the goal for different directions. So general. So the conclusion is okay? Yeah, for this building.
For this building, yeah. It's because the difference in stiffness between the concrete cell and the rock surrounding it and underlying it is not that big.
That's pretty different again than the depth of the concrete.
Yeah, the depth is not that big.
So how much concrete embedded in the rock over there? How come it's like 60, 70 feet? Embeddment?
I mean, the two concrete is 60, 70 feet.
Yeah, perhaps it would help if you have a little, like a little cartoon of
actually, you can, I don't have specifically the link, but it's like in the and
And that would help visually.
Yes, it will be
No, you don't really see it there.
basically this model, I think the last 2 or 3 are an interpretation. I don't specifically say that.
So, how many layers of brick or concrete fill domes are underlying the bottom of the basement?
2, I think.
2.
The building, the final one is the soil, basically at the top. This is fully made special. The other one is the 2 concrete around the building, and then the last, the 3 under. That's the foundation. The fill material is not very wide.
Okay. And this is the in-situ rock. This is the in-situ rock. And this is backfill, very small backfill. And this is the building on top of it. 3 meters, or is it 3 meters? No,
So we can go to the next
it's like 5 meters, right? 5 meters. And so it's 5 meters. And then
Next one. Next question 17 is related to the structural evaluation. That is to demonstrate that category 1 structure, defining category 1 structure decided for the basically, we did a simplified conservative way to do that. And in this other equation, we are asking to provide more detailed evaluation based on direct stress calculations, now the scaling factors that we were using, and to consider the process interaction between different load components like axial, shear, then we are asked to demonstrate that the resulting site-specific total stress demand, which includes seismic loads plus other applicable loads, are bounded by the code allowable in all cases. Also, we were asked to provide site-specific load demands and evaluation of reactor pressure vessel and other components and supports in anchorage to building systems. We demonstrate the adequacy of conservative approach. Basically, what we are going to do is we will take instead of scaling the stresses as a total, we will look at different components of the load, how they are scaled, how much amplification we have. Basically, we will focus our attention to the members which see higher loads than what the VTB considered. So basically, we will scale those loads, and we will use the SSDP program, which was used for design or checking of these reinforced concrete members, to show that the stresses will be calculated using this conservative scale factor is actually conservative.
Can you explain that scale factor? Because this is a different scale factor from the one that you were...
Exactly. What we were using previously, we would take input from all the load components, which one has the highest amplification, and we took the traces which were presented in the DCD, and we scaled the total based on that maximum scale factor. Now, I understand if your concern is that reinforced concrete is non-linear, and there's no linear relationship between the axial force and the
combination of the different forces.
So basically, we're going to address the non-linear part of the problem by scaling the actual cross-sectional moments and shear forces and axial forces. And
by what?
By whatever the load was not amplified. So the axial forces will take.
Well, see, that's the question that I have, because we're talking about two different models here. We're talking about a stick model, and then for the design, there's a separate finite element model. So which one? So you're taking the results from the site-specific analysis of the stick model. You ratio those values to the relative to the DCD results for that same stick model. And that's a scale factor, but that scale factor is going to be different for every element in that stick model, or every member force.
Every member model, I mean,
right. So every member force in the stick model is going to have a separate ratio, right? Okay, so that's as far as the stick model goes. Then what ratio? So how are you translating each of those ratios to the results of a Nastran analysis? That's what I don't get. I mean, there's a disconnect there.
Basically, for the axial force, we do the axial amplification.
And now we're talking about a big finite element model with plate elements, brick elements, and so forth. Are you applying those scale factors to like cross-sectional resultants, or I just
before we go and check the cross-section, we have results for the axial force. The shear. So we know how much the shear, how much larger is the shear now for no kind of. And
so that's the cross section of the entire structure, right? Not an individual element. How are you going to do that?
Yeah, but because you have linear, you have the load. The load went down. The distribution of the load is through the structure is linear. So if you, for example, if you run an analysis, you have one shear force, I mean, horizontal force applied, then you calculate some distribution to different forces. Now, if this shear force goes higher, the shear force in each force will go for the same proportion higher, right? Because it's a linear relationship.
You have several floors, you know.
Yeah, I mean, this is complicated model.
I don't know how to do it.
Yeah.
I mean, even if we go reiteration, we will base the load based on the maximum using the methodology the same. Developing the load based on the shear force in the linear.
The Nastran model is a static model, right? It's not time dependent. So the loads that you impose on that were imposed on the Nastran model at the time it was run during the DCD phase, those were equivalent static forces that were applied. So they were maximum accelerations that were immersed. I mean, whatever was done for DCD, but somehow you got results from the STIG model, that's the time history results. And those were transferred to the Nastran model, which is a static analysis. So it seems to me that as long as the scaling factor sort of captures that, how that process was done, I mean, it's not clear to me how the scaling factor sort of, there's a one-to-one relationship between the scaling factor that you're coming up with for each member force in your STIG model. And
for example, I did some analysis for the flat, and actually this was the most critical where we have the lowest margin. And in that class, the vertical acceleration was magnify the same 20%. I don't know exact number. So what we did, we increased the bending moment by 20%. And we rerun the SSTP analysis to see what kind of slip it is. The actual forces will stay the same.
All right.
Did I found it?
Well, no. I mean, I think
This is an important part.
yeah. I mean, I
we need to understand.
I think what you're basically skipping the next trend analysis, and maybe
to share the distribution in the element level.
yeah. So you're keeping that.
How are you doing it? As I said, you're coming. You're only non-linearity. It's not really non-linearity, but when you have interaction between different rate components, when you check. That's next factor, right? That's not the increase the scaling will go away because it's not linear. I think my world's concern, let me try to understand.
Yeah.
DCV uses the equivalent static approach, like the two-stack approach, right? You do SSI analysis, you develop the maximum accelerations at different flow levels, right? And you apply the maximum to a static model, and then use that model to generate the elements of stresses, forces, shear, and axial whatever demands, right? That's a DCD approach, right? Now you have a set-specific analysis. I think the issue is when you perform a set-specific analysis, are you still maintaining the consistency in terms of methodology used in the DCD? Are you also identify the maximum acceleration at different floor level from the set-specific analysis and use that to develop your whatever skill factors? So then your skill factor would be a ratio of the maximum acceleration at each particular floor level from set-specific analysis to the stick model at the same level of an DCD analysis, right?
This is correct.
And then you have to apply that. That will be the ratio applied to that floor level across the board. Right? For the
Exactly right. Exactly. I mean, I think it's more complicated than that in the DCD, but without getting into the details of how it was done in the DCD phase.
Right. I'm talking about this skill aspect.
Right.
You know, the ground motion. You know,
right. It's precisely that how that's done. I'm not sure that stays always linear because your maxima in the DCD phase may have occurred at a certain instance, and your maxima in your site-specific analysis.
In this case, you're using equivalent static approach.
You just apply one load.
But you lose the phase. I mean.
Yeah. Okay. Exactly.
No, but if their analysis, that specific analysis, okay, use the same approach, then they also lose the phases. So it doesn't really matter what the phase.
But
the phase are out of phase, maximum occurred at what time.
Right, but the key thing that they're doing is that they're skipping that phase. They are not rerunning that, or they're not repeating the process of extracting equivalent static forces from the stick model, applying them on the Nastran model as static forces, and then obtaining that result. They're not going through that process.
Right, yeah.
They're not going through that process.
Right, but I'm not why you need it goes through. That's what I'm trying to understand.
Yeah, I'm trying to understand it too.
Yeah. DCD is based on the input to
that's right.
Static model, right? It's based on the SSI analysis, and then you use the maximum acceleration by floor level. You basically ignore the thinking effect, which is considered conservative, right? And now you have that specific analysis, which is basically doing the same
type of analysis and generate the maximum acceleration is 4, and you ratio the two values.
Yeah, see, where it gets complicated is because now you have different ratios for each member force, right?
Right.
So, okay, that's fine. Yeah, different ratios, site-specific relative to DCD,
Right.
and now you have to apply those different ratios to a set of stress results that came out of the DCD. So how do you actually do that?
Basically, just for clarification, the first step we already did.
Yeah.
We took the loads, we developed those for no damage, which we call low demand, and we compare. So what we are skipping as a step is the actual number.
Right.
So why we are skipping it? Because we already know the load, we know the ratio, and now those loads and the member forces,
Yeah.
something traces later, are proportional because it's a linear. So we
Yeah, but the complication is though, okay, so you have a whole set of ratios, right? And now you have a set of Nastran results. So you have a set of element forces or element stresses. So now you got to figure out which ratio from the first part of your effort, which ratio corresponds to what stress result.
you mean internal force.
Yeah, or internal force, right? You got to figure out, okay, the moment of this elevation went up by 30%, let's say. So now I got to apply that 30% increase only to whatever force resultants I get in the Nastran result by 30%. But for the axial load may have gone up by 50%. So the axial results from the Nastran analysis need to go up by a different factor, like 50%.
Let's look at the shear. The main
I mean, it would be easy if Nastran were just a stick. Then you just map each one by one, but it's not. So that's where I get confused.
Exactly. We go, let's take the shear one. We know that the shear force went up 30%. Then the shear component, the shear stress will go 30% up. Now, the aspect went up 50%, then you actually reduce it because it's not conservative. Then when you have compression, the strength shifts up.
I think what we did was we took the worst case for all
I'm sorry, we can't hear.
They use just one scale type.
I think what we did was we used, and I should probably need to confirm at 10 o'clock, but we took the worst of all the seismic increases for all of these forces. So if the moment had the highest increase in seismic, that was the largest delta that we took and applied it to all of the other forces in the Nastran. So
At that floor.
At that floor. So we went element by element, floor by floor, and evaluated which was the highest delta. So it was a very conservative approach. We took the worst case and applied it across the board for all of the forces in the Nastran. So we really did a very specific, correlation, and Aishan helped.
Yeah, but see, the problem is that, okay, so you wanted to capture the worst state for shear, the example that you're thinking. So I increased the demand by, say, 50%. So I assume that all the force resultants at that elevation go up by 50%. That means that the axial force also went up by 50%, and if that was a compression, the level of stresses are actually helping you. And if it was a tension, then you're in bad shape. So how do you...
So we're going to answer that portion in our RAI response. We're going to do another SSPP analysis to prove that the concern that you have about the nonlinearity from the interfacing of the axial forces and the moments, that portion of that issue is going to be clarified in our subsequent REI response. But just to answer that, the question that you have about how we applied it, we went elevation by elevation, looked at all the forces, and then took the worst case from the DCD model